going to be talking about liquids and their physical properties in this chapter. So let's get started. Okay, so states of matter. We already talked about gases there. That's a little better. So we previously talked about gases. Remember, some of their properties are they have an indefinite shape, an indefinite volume. And when we were talking about kinetic molecular theory, particles of gases are far apart, move freely, and they don't interact with each other. What we're going to talk about now are liquids, and liquids have an indefinite shape. So they'll take the shape of your container, but they do have a definite volume. And it turns out the reason they have a definite volume is that they are close together. They're not very close together, but they're close together, but they can slide past each other. So they do have interactions and attractions with each other. After we finish talking about liquids, we're going to talk about a little bit about solids. And solids have a definite shape and a definite volume. And all of the particles in a solid are very close together. They can't really move past each other like in a liquid, so they're pretty much in place. Okay, and we have two types. We have crystalline solids or amorphous solids. Crystalline means that it has a regular 3D geometric pattern to it. Amorphous means it doesn't have a 3D geometric pattern to it. Okay, so changes between states of matter. So what happens is, if I go from a solid and I become a liquid, we call that melting or liquefying or fusion. Okay, if I'm freezing, I'm going from the liquid state to a solid state or solidifying. Okay, now when you look at this, remember liquids have higher energy, they can move past each other, whereas solids have a lower energy, so they can't move past each other. From a liquid, I can go from a liquid to the gas state. And when I do, you could be boiling, you could be vaporizing or evaporating. Those all refer to going from the liquid state to the gas state. If I go from the gas state to the liquid state, I'm condensing. It's condensation, or I'm liquefying. I can go from a solid state to the gas state directly and bypass the liquid state. When I do that, that's called subliming. If I go the other way, that's called condensation. Okay, so from the gas state, that's called deposition. I apologize. So going from the gas to solid, it's deposition. Okay, what we're going to talk about then is the intermolecular forces, the attractions between the molecules that actually hold them together. Okay, now when we talk about it, we're going to mention Coulomb's law. And basically, it's a constant times Q1, Q2 over R, and that's the energy between two oppositely charged particles. If Q1 and Q2 are the same charge, then it's the energy where you have repulsion. If it's an opposite charge, then it's attraction. The ones that we're going to look at are London dispersion forces. Sometimes you'll hear people talk about van der Waals forces, but we call them London dispersion forces because we want to be very specific about the ones we're looking at. Dipole-dipole interactions, hydrogen bonding, and then ion-dipole interactions. So let's look at our intermolecular forces. The first one down here are your dispersion forces. Okay, and if I can get this. Okay, so what we're looking at for dispersion forces is basically temporary dipole interactions. Okay, get a pen here. So it's a temporary attraction between two molecules, and what it is caused by the formation of a temporary dipole. So this is my molecule, my nucleus, and I've got my electrons around it. At some point in time, all your electrons are going to be on one side, and that gives it a partial negative charge, and the other side is going to be partial positive. Now, it's not a stationary dipole. It's temporary, it goes back, those electrons are moving all over the place. Okay? Now, London dispersion forces are the weakest of the intermolecular forces, and when you look at what happens is if my electrons move here and it's delta minus, that's delta plus, then it's going to repel the electrons and leave that sparsely populated with electrons. So it's going to be delta minus, delta plus. So we now have basically a temporary attraction between the two. Okay? It's the weakest of the intermolecular forces, and it's going to increase. The larger the molecules, the more surface area of contact, and so the greater the London dispersion force. Okay? So how can we see that? We see that if we look at the boiling points. Okay? If we look at helium, helium is the smallest, okay, of our noble gases, and the boiling point for helium is nearly negative 270. That's 275, so it's almost 273. Okay, so it's very, very close, just a little bit above actually my absolute zero. Okay, now if we get to larger and larger ideal gases, remember ideal gases have no permanent dipoles. The only thing is the temporary dipole that's produced by the electrons. And you can see as I increase my size, because of the polarizability of those electrons, right? Remember, polarizability is the same as the squishiness. So you can move those electrons more easily, something like radon and xenon, than you can in helium and neon. You can see that my boiling point has increased. Okay, and that's because I have a greater surface area, and so I can have a larger London dispersion force. Okay, take a look at a few other examples. Here, we're looking at methane, 1 carbon, 2 carbons, 3 carbons, 4 carbons. And you can see that as I increase in size, I go from a negative 161.5 degrees Celsius for my boiling point to a negative 0.5 degrees Celsius for my boiling point. So as I increase in size, my boiling point increases. Okay, but what happens if I have the same size? Okay, so if I have the same size, so both of these have 5 carbons and 12 hydrogens. This one I have a carbon in the center, and it's surrounded by carbons with 3 hydrogens on it. This one I have 5 carbons in a line, and then the hydrogens on them. And you can see this is almost like a little sphere. It's a little beach ball. And so when I have these two interacting, there's not a lot of point of contact. So you can see that even though I have the same molar mass, this one, the neopentane, has a boiling point of 9.5 degrees Celsius because they don't have a lot of surface area. Look at this. All this is surface area. If you look at this line, that's like half my pen. This one is only about a third of my pen. And this one has a boiling point of 36.1 degrees Celsius. So just that increase in surface area is enough to increase my London dispersion force and give me a higher boiling point. What about another intermolecular force? Let's talk about dipole-dipole interactions. Remember how we talked about molecular compounds being polar. If a compound is polar, that means it has a dipole. There's a permanent directionality where one side of my molecule is slightly positive and another side is going to be slightly negative. Okay? So when I look at a dipole-dipole interaction, let's give you some examples here. Okay, we mentioned already that a polar molecule, and remember we talked about the geometry and how the differences in electronegativity that tells us if we have a permanent dipole. We have a permanent separation of charge. That's why I have, it's like a weak magnet, plus and a minus, or north and south. So let's look at water, acetone, and acetonitrile. Here's water. My hydrogens are slightly positive, my oxygens slightly negative. Why in this direction? Because remember, it follows the bond here, follows the bond there. And if I add the vectors, the directionality of my dipole will be straight up. My carbon-hydrogen bonds are nonpolar. Carbon-carbon is nonpolar, but carbon-oxygen is a polar bond. So acetone has a permanent dipole from this carbon, slightly positive, to this oxygen, slightly negative. Acetonitrile, carbon-hydrogen, carbon-carbon are considered nonpolar, but carbon-nitrogen is polar, where the nitrogen is pulling the electrons toward it. So slightly positive carbon, slightly negative nitrogen. So what happens is this. Let's take acetone, for example. Acetone has a positive carbon right here and a slightly negative oxygen right here. So I can line up my acetone here where my oxygen, which is slightly negative, is close to my slightly positive carbon. That's one orientation. But there's another orientation. That is here, my oxygen is directly in line with the delta positive of my carbon. So there's this orientation, this one, they're apart. They're like standing staggered. This one, they're directly in line. Or you can have an orientation where this acetone is upside down. So this slightly positive carbon is near the slightly negative oxygen. This slightly positive carbon is near the slightly negative oxygen. So these are all examples of dipole-dipole interactions. And in particular, this is an example of acetone. Okay, so the next intermolecular force that we're going to be looking at, let me just try to get this in the right orientation for you, are H bonds, or hydrogen bonds. One of my personal favorites. Okay, so hydrogen bonds, it's actually a partial bond. It's not a true covalent bond, but it's a partial bond between the lone pair of oxygen, nitrogen, or fluorine with a partially positive charged hydrogen. So let's look at ammonia. If you look at ammonia here, see how nitrogen is pulling the electrons away from the hydrogen, which means my hydrogen has a slightly positive charge to it. Remember, the difference in electronegativity is greater than 0.4. Okay? Now, I have something that's positive here, and I'm next to a lone pair. So this hydrogen can form a hydrogen bond between the lone pair of the nitrogen and itself. Okay? Let's take a look at water. There's a lone pair on the oxygen, two lone pairs. Oxygen's delta minus, hydrogens are delta plus. So I can form a hydrogen bond between the lone pair on the oxygen with the slightly positive hydrogen. But when we talk about hydrogen bonds, we're not restricted just to a hydrogen bond between two molecules of the same substance. You can do it with different substances. Okay? In this case, if I have water and ammonia, then there's the lone pair of the nitrogen here that can form a hydrogen bond to the slightly positive hydrogen on the water. As well, the lone pair on the oxygen can form a hydrogen bond to the slightly positive hydrogens on the ammonia. So we can have hydrogen bonds for substances with itself or substances between two different substances. Okay, now how do we know oxygen, nitrogen, and fluorine? How come we didn't pick sulfur or chlorine? If you look again at boiling points, you can see methane. If you look at the period, so there's a carbon, silicon, germanium, okay, and tin. If you look, there's a very linear trend to it. So the only thing that's contributing here is basically your dispersion force. Here I have some dipole, HCl, HBr, HI, But we have these unusually high boiling points. So why are water, HF, and ammonia, why do they have such high boiling points when the trend seems to work so well for everything period 3 and up? The only way that can be explained is that hydrogen bonds occur only for oxygen, fluorine, and nitrogen, not for chlorine, not for phosphorus, not for sulfur, not for silicon. And that gives it the extra interactions and attractions between your molecules, making your boiling point that much higher because there's that much more energy needs to be put in to break those bonds to get one of your molecules out into the gas phase. Okay, the last of the intermolecular forces is basically ion dipole. Okay, and we see this when we dissolve our ionic compounds. Okay, so an ion dipole, basically, my chloride has a negative charge, and I have all these water molecules, and all the hydrogens with the delta positive charge on the hydrogens will actually interact, forming a ion dipole attractive force. Likewise, sodium has a positive charge, so all my oxygens of the water solvent that's slightly negative will form ion dipole attraction, okay, between the two. Right? So let's take a look at how strong they are. Okay, the weakest, as we mentioned earlier, are London dispersion. They're only 1 to 10 kilojoules. And remember, a hydrogen bond 10 to 40, it's about a 15th to a 20th of a true carbon-carbon covalent bond. So you can see how weak these are, 1 to 10. And the 10 is unusually large, and a lot of it's going to depend on having a very, very large molecule. Okay, so the weakest of them is going to be London dispersion, followed by dipole-dipole. These only occur between polar molecules, where these occur for everything. Any substance that has electrons, so that means all matter, will have London dispersion forces. If I have polar molecules, then I have London dispersion forces and dipole-dipole forces. If my molecules are not only polar, but it's got polar bonds such that I have lone pairs from oxygen, nitrogen, and fluorine, and slightly positive hydrogens, I'm also going to get hydrogen bonding to it. And we actually see hydrogen bonding. So if you look at DNA, and you look at your two sister strands of DNA, they're held together. Part of what holds the two strands of a DNA molecule together, okay, a duplex strand, are hydrogen bonds between your bases. And those are going to be between hydrogen, oxygen, hydrogen, and nitrogen. Okay? So those are fairly moderate. And then the ion dipole, those are moderate forces between ions and polar solvents. And that makes sense because otherwise, if they weren't moderate forces, how would we end up dissolving table salt in water? So they have to be strong enough to overcome the ion-ion attractions that are in solid salts. Okay, so let's stop here and start the next series of slides where we cover select properties of liquids.